In this video, we are going to work on flocking or boid algorithm, which is used when you are working with a large group of game objects, or in this case, enemies, and this will create more realistic movements. In normal cases, the enemies would go into one position, but with the flocking algorithm, you can see they are keeping the distances and they are moving more naturally, and they can surround also the player nicely, and they can keep distances when they are following the player. So this will be the task for this video. To get the starting project, go to description of the video, click get a project, download and unzip the file, open Unity Hub, click add project and select the unzip folder, open it. In the project view, select scenes, double click sample scene. Now you are ready for the video. The current state of simple follow functionality is that the enemies or the objects that are following you are merging into one path. So we need to implement the separation algorithm or boid algorithm. We need to apply some separation forces if the enemies are close to other enemies. Okay, open your enemy, click on the enemy, and you should have an enemy controller. It's not visible. I will just move it up here. All of your enemy should have an enemy controller. Actually, I need to go to the prefab view. So here in the assets, open game SRC. Hopefully have the same structure of the project. That was the instructions in the video to download it or to get it from the GitHub repository. So you're in this state. So in the prefabs, you have an enemy. See here, and the enemy has an enemy controller. Just move it up here so it's more visible. Enemy controller. Just click here 3 dots, edit script, so it will open Visual Studio Code. Actually it should open, but it didn't open, but here it is, enemy controller. This is the implementation we have done together in my other YouTube video. You should be in this state if you downloaded the project from the link in the description. Okay, so we'll be extending this functionality. So for the boid algorithm, it's important first to detect all of the neighbor units. So your enemies, as they are running together, these enemies, I'll go back to the scene view. As they're running together, we should detect the neighbors. So if they will be running together in some distance, for example, this enemy here, I will open my drawing tool. Okay, we'll be detecting the enemies in some radius. Let's say like this. Maybe that will be the radius, and this radius will be detecting all of the enemies that are close. Or maybe in this radius. All right, detecting all the enemies. So in this case, I will detect this one, and this one. And in this case, I would apply some separation forces. Okay, so I would go straight to the target, but I somehow will normalize the forces in which they are moving. So they wouldn't be moving into, let's say, the same path, merging, but they be moving to some average path. All right, and it would be keeping the distance. So some separation forces would be applied to them. But first we need to start simple. We need to detect the neighbors, right? So let's do it. Go to your enemy controller, and we'll start here in our follow target. Okay, down here, he will be implementing this algorithm. So first thing is to get all of the neighbors. So I'll write here var and neighbors. All right, equal, and I'll call here function get neighbors. Get neighbors. Okay, of course we don't have this method, so we need to implement this. So I'll just hover, quick fix, or just simply implement this. Whatever is faster. Here we have it. Get neighbors or detect neighbors. Whatever name suits you better. This should return something. You see, it's returning the object. But what we'll be returning here will be actually array of colliders. So right here, collider and array. Remove this throw exception, and because we will be actually detecting here the enemies. First, we need to somehow identify the enemies, and we will put all of the enemies into the same layer. So go back to your scene here. Click on the single enemy here. Doesn't really matter which one you are clicking on, and you can see the layer on the right side. The layer is default. Go to the add layer, click add layer, and create here a new layer, call it enemy, this way here. Now go back to the enemy, and click here layer, and now again, let's add here now this enemy you have created. Okay, click it, and right here, yes, change children. And now to apply it to all of your enemies in the scene, here we have a prefab, and we need to override it. So click here, overrides, Open it and click Apply All. Now when you will select any of your enemy, select it and make sure that all of the enemies have a layer enemy. Very important. Now we can go back here and we can get all the neighbors. So first we'll get here this mask we have created now. You can get it like this. Let's write here var, call it enemy mask, and assign to this, let's access here layer mask. And on the layer mask you have a function called get mask, and you are looking for the enemy. So this will get you your enemy mask or enemy layer. And we'll be checking all the enemies with the overlap sphere. So how this works, I will show you. Let's write here return and access your physics. And on physics you have a function called overlap sphere. Overlap sphere. You want to provide a position at which you want to cast this sphere. So transform.position. And then what will be the radius of the sphere? And the radius of the sphere will be defining in the fields here. And I will create here new fields. I will write here header. And header will be separation algorithm or boids. Why it's actually called boids? Did you know? I just Google for it or search on the internet for it, and boids is because of birds, how the New Yorkers pronounce birds, boids. And the creator of this was some software engineer that wanted to create simulation of the birds and separation of the birds, how they're moving in the flock. And that's why he called this algorithm boids, like birds in New Yorkers accent. Okay, small funny detail. Okay, so boids, and we'll create here a serialized field, private float, and we'll call it detection distance, m_detection distance, and default will be, let's say, 1 unit. Of course, we can change it. Now we go back down here, and overlap sphere will write this detection distance, and we want to write here enemy mask. So this will be detecting only enemies. We'll be detecting only objects which have a layer of enemy. Okay, now we can save this. We can go back to our code, and what I want you to imagine when this will be called is that on every enemy there will be sphere casted. So you can imagine at the start position of the enemy here, on the start position, there will be sphere casted with a radius of 1 unit. On every enemy it will be. And it will, if it will intersect with the collider of any other enemy, then it will detect this enemy. Okay, and it will return it. So this will be, I think, that big. 1 unit, it will be that big, maybe even lower. So the enemies, they will be running towards the player. They need to get closer in order to detect it. Okay. So now, all of our enemies on the enemy controller, there should be boids and detection distance. You see one, we can play with it and we can change it. If we want to actually see if you're detecting any enemies, we can just do a small check. If you want to do anything like this, you can just write your public field so you can see it actually in your editor. Public, let's call it neighbors count, and initialize to 0. Let's write here public int neighbors count. And here, as you're getting the neighbors, let's write here neighbors count equal neighbors dot length. And now on each enemy, you should see how many neighbors it has. So I will start a game. You will see in the player controller now you have a neighbors count is 0 currently. Don't change it. Stop the game initially like this. Play the stop button and play this game, so it will start in the stop stance. You can see nothing is happening. And play the play button, so you can see they will start moving towards the player. But you need to click to move the game because it stopped. And now you can see neighbors count on each enemy. So for example, when I select this one here, it's selected. You see here on the right side neighbors count. So this is detecting only 1 neighbor. Okay? And I can check every enemy like this, but you can see as they will get closer to me, maybe it will detect more enemies. You will see as they will be merging to the 1 position. I will be clicking, and you can see already neighbors count is already 2. as they're getting closer to each other, and eventually it will detect all of the enemies as they will be getting towards the player. And now 4, 5, 6, 7, 8, 9, 10, and all of the enemies will be detected eventually. So now we are getting correctly all the neighbors. That's how it works. Okay. If you want to debug things, that's a very good way. Just create a public field and just assign the value to it, and you will see in the editor how it's changing. I will remove it because we don't really need it. We have here neighbors, we know that we are getting. So that's the first part of the algorithm. Get all of the neighbors. Perfect. Now we want to calculate the separation forces. Okay, sounds difficult. It's not really not that difficult. Create here a new private field, vector3, and this will be m underscore separation force. Okay, at each run of our update loop in a follow target, we will restart our separation force to be 0. So here will be separation force, and we'll just initialize it to 0. So it will not accumulate over time. That's very important. We need to every time restart it when this is called over again. Okay, now we will be creating a separation algorithm, but the separation will be applied only if we detect some neighbors. So we'll write our if statement, and we will check here if the neighbors length is greater than 0, only then we would like to do some things. And things, what we want to do is first calculate separation force. So here we want to calculate separation force for all of the neighbors here. So we'll be passing all of the neighbors here. I'll hover over quick fix and generate method. Now we have here calculate separation forces, and we are getting here all of our neighbors, okay, as a collider array, as you see here. Okay, so how this actually works. So first of all, there are multiple steps. I'm not sure if to write it down or not. Okay, let's write it down as the comments. First, compute the direction to the neighbor. Okay. In the second step, we'll get a distance from the neighbor. Distance from the neighbor. I don't want to write the entire thing. I'm too slow. So here, calculate direction to the neighbor. And now, very important thing. We want to get away from the neighbor. We want to do the separation. So we want to separation force will be calculated away from the neighbor, so they are not stacking together. So as we calculated the direction to the neighbor, we would like to get the opposite vector of this. So let's say the direction to the neighbor. Here is the enemy neighbor, and here is my enemy. This is a direction vector. We would like to actually calculate the separation force. We would like to get the opposite vector. So calculate opposite vector. Calculate opposite vector. Okay, and then we will check if the distance is greater than 0, then we will be accumulating the separation force for all of our enemies. And to scale them, we'll be dividing them by the distance. Okay, so I'm going to implement this, and we'll be talking about this as I'll be implementing it, okay? So calculate the direction. So first, we need to iterate over all of our neighbors, right? So for each, and let's write here var neighbor in neighbors. Okay. So now for each neighbor, we want to calculate direction. Direction is very simple to calculate. These are neighbor position minus our position. So neighbor transform position minus our position is the direction to the neighbor. Distance is also very simple to get because the distance is just the magnitude of this direction. Okay, and the away force is also simple to get because away force is just the opposite force of the direction. And the opposite force is just the negated force of the direction. So minus direction will get you opposite force. And you want to normalize all the forces so they are equally, they are same size. So you are usually normalizing this. Okay, so you normalize it to get the same sizes for each direction. And now, if the distance is greater than 0, then you are computing the separation force. And separation force is simply accumulation of all of the forces of your AV forces for each of your neighbors divided by the distance. Okay, so now, first of all, we are writing this check if the distance is greater than 0, because we cannot divide by 0. So if the distance would be 0, you would get here error. So that's why I'm checking the distance is greater than 0, only then divided by 0. But why we are dividing it by the distance? That's the question. The explanation is very simple. The further we are, so the distance is larger, we want to apply smaller force. If we are closer, we want to apply the bigger force, and this operation is reflecting this. So consider a simple example. When, let's say, AVA is like just 10 value, doesn't really matter what, but the distance is 10 units. Okay, so divided by the 10 units. So 10 divided by the 10 is 1. So let's say separation force would be 1. Okay, but if we get closer, so the distance would be only 1, we are very close, 10 divided by 1 is 10, so the separation force would be 10, so you can see it's much bigger. That's this operation what we are doing here. Closer we are, stronger the force should be. And that's it. That's the separation force. That's how you calculate it. Okay, now when you have a separation force, you can go to the step 2, actually step 3, because the first step was to get the neighbors. Okay, so we'll just mark it down. So get neighbors was step now 1. Okay, step 2 is calculate the separation force that we have. Now the third step is to apply alignment. What is the alignment? Okay, so the next step I will go here and I will first create a method and I will be talking about it. So let's create here method apply alignment. Apply alignment for all of the neighbors like this and generate this method. So quick fix and generate method alignment. So what this is basically doing, imagine here player and then you have enemies. Let's say this is one enemy, here is the other one enemy, and here is the other enemy. And all of them, they have some directions that they are facing, forward directions where they are currently moving, and they should be facing to the player, right? All right. So what you want to do is actually, let's say for this enemy, you want to detect the neighbor, and you want to detect all of these forward forces that are moving. And what you want to do is average them out. So force down here and down here can be maybe this direction. And this you want to apply to the separation force. Okay, so simply understand it like this. Get their direction of the neighbors, average them out, and apply to the separation force. Okay, that's what is the alignment. So in apply alignment, all the neighbors, we will create here a new variable and we will call it neighbors forward average, or maybe shorter. Let's write here first vector 3 type and call it neighbors forward movement, or let's get just neighbors forward, doesn't really matter, and default will be vector 3 0. Now as I told you, we'll get all of our neighbors, so for each again, and we will again copy it from down here. Okay, so we have all the neighbors, and we would like to get all of their forward directions. So we'll get the neighbors forward, and we'll accumulate all of the forward direction of the neighbors. So we'll get simply the single neighbor in the iteration, and then transform forward. That's how you accumulate all of these into neighbors forward. So that's the entire the vector accumulation of all of these all the single neighbors. Okay, that's it. That's it. Okay, and then we'll add the if statement, and you will check if your neighbor's forward vector is not equal to vector 3 0. So if this neighbor's forward vector is not equal, so we have accumulated some forces, vector 3 0. Okay, then you want to normalize it, and this basically average it out. So neighbors forward and call here normalize, and this will normalize it. So this will get you the average size of this vector. which is the sum of all of the parts of all of the neighbors. And then you will apply it to the separation force. So get the separation force plus equal neighbors forward. Oof. Okay. And now finally, not finally, but this is just a third step. We still will be missing one more. Third step will be, oh, this is a fourth step already. 1, 2, 3. Okay, that doesn't really matter. Okay, now when we are moving forward here you have a method to move forward, and we are just currently applying only direction to it. Now, instead of applying just a simply direction, we will get here a variable and we'll call it combined direction, because this will be direction plus the separation force. So we will get here our original direction like this, equal m underscore direction plus underscore separation force, and we'll normalize it. Okay, so we have this combined direction, and now in the movement we will be computing, it will be not a direction, but a combined direction multiplied by the speed multiplied by the time delta time. Okay? And now we can test it out, but before that I will just verify that everything is at the place. So here we are calculating the separation force, getting the neighbors, calculating separation force, applying alignment. Yeah, that seems fine. Let's save this. Go back here. Current detection radius for our enemies is 1, which is maybe too small, but let's see how it will look like. So already the movement should be better, but this will not work still completely. Okay, we are not done with the implementation, but it should look at least a little bit different. You can see, yeah, there is some for sure there is some separation applied. Yeah, there's definitely, you can see it. And there is a separation applied. Okay, our enemies are behaving 100 times better. Okay, yeah, that's actually a very valid solution, as you see. There are small tweaks we can do because these enemies on the outside layer, they're still running at a place, but we can deal with this later. But the movement, as they're following us, is much better. Okay, we can stop the game and we can do some more improvements. Guess let's go to the coding editors. The next step is to apply cohesion. Okay, so the next step after alignment is to apply cohesion. Cohesion. And also pass here all of the neighbors, and we'll generate method for it. So let's hover, quick fix, and cohesion, apply cohesion. So now we have it. So what is the apply cohesion? How this will apply to our separation forces, what we are applying to the movement. So cohesion is basically this. When you have multiple enemies, you detect the neighbors and you will get all of the positions of them, and you get the average position. So all of the enemies are going to the center of the group, basically. Alignment is to just align enemies, but the cohesion is to move them to the average center position. What I mean by that? Imagine, I think it will be better like to write it like this way so you can see it. You have 4 enemies close to each other. So this is your axis in the system, and you have 4 enemies close to each other. So here is, let's say, 1 enemy. Here is the second enemy, other enemy, and 4 enemies, and they are detecting each other. Let's say this enemy is at the position 0, 0. This one is x is 1, y is 0. This one is 0, 1, 1, and then this one is 0, 1. That's the coordinates of them. So you'll add them together, all these positions. So when you add this together, this position, what it will get you? So you need to add each part separately. This will get you position 2, 2. This position you will divide by numbers of all of the neighbors. So 4. This divided by 4, you need to divide each part by 4, this and this. This will get you position 0, 5, 0, 5. So 0, 5 and 0, 5. 0, 5, 0, 5, where is 0, 5, 0, 5 here? So 0, 5 is in the middle here and here. So this will get you position exactly in the middle. So, and that's the force you will be applying the separation force. So you have a sense of cohesion. So you're moving to the center of the group. Okay, because exactly in the center, and we'll be applying this force, this direction to the center of the group to the separation force. And this will affect also the movement. Okay, let's apply this. It should be also simple. When we know how to work, how it works, so we'll go to all this for each, because we need to again get through all of our to all our neighbors. We will write here new vector 3, and this will be, let's say, average position. Average of I'm spelling correctly. I have always problems with the average. I think like this. Average position, again, vector 3, 0. Vector 3, 0. Now to get the average position, just get here average position and neighbor transform on forward vector, but we are going for the position now. And now average position, to get it, we just get a average position and divide it by all the neighbors' length. And it will get us the average position. And now we can compute the direction to this position for our enemy. So let's write here vector 3 or var, whatever you prefer, and cohesion and direction like this, and this will be the direction towards this position is the average position minus our position, and normalize it. Normalized and apply to the separation force plus equal cohesion direction. And we are calling the apply cohesion here, perfect, and we can save this and we can try to see. Maybe it will screw up our algorithm a little bit for now, but because we need to do some changes, but we should see already some results. Good or bad? Let's see. Yeah, I think it's a little bit better even now. Okay, so now we can improve it even further. So what will be other improvement would be this some weights or some scalars for these forces, so we can affect, maybe we can lower the separation force, and maybe we want to increase the cohesion force, and so on. So that's why we are going to implement some scalars or weights. This should be simple steps. So let's try this game down, go back to your coding editor, and for our boids here, we'll create new serialized fields. I will copy this one here, I'll paste it, and I will call it separation weight. Okay, so m underscore separation weight, and I will copy paste it 2 more times, because the second one will be not the separation weight but the alignment weight, and the last one will be cohesion weight. When the weights are 1, we are basically not applying anything. We are not applying anything just yet, because we need to go up now to our algorithms. So first to our calculate separation force, find it. Calculate separation force, and as we have a separation force here, we will multiply it by the separation weight. So here, like this, and multiply it by m underscore separation weight. Make sure you have a separation weight here. When the weight is 1, everything multiplied by the 1 is the same number, so we are not doing any changes, but in editor we'll be changing it. Okay, now what's the second one? So second step was third one, right? So apply alignment. So here, as we have here this neighbors forward, here we can multiply by the alignment weight, and the last cohesion, where we have a cohesion to cohesion direction multiplied by the cohesion weight. Okay, so we shouldn't detect any changes just yet. Just verify everything is correct here. It should be. Okay, let's save this. Get back here. There shouldn't be any changes because all the values are 1. So when I will play this, this will work the same. Okay, but you should see changes when you will go to your enemy and change the values. Let's say our separation weight will be 3. And if you want to apply it to all of your enemies, you need to override. So apply and apply all. So this will apply to all the enemies. And now separation force, you can see they're moving much faster from each other. You can see they are staying separated further from each other because the separation force is very strong, and they're never getting closer to each other, as you see here. Maybe you can decrease the separation force. So separation force to 0.5, so you can see effect of it. Again, when you change it, overrides and apply all to all of your enemies. Okay, so this is, you can see that now they're sticking closer to each other. And this is actually, that's very good. 0.5 works really, really great. Maybe even increase it. If you want to apply it again without clicking here overrides, just go to your game SRC, prefabs, enemy, double click enemy, and just change it here. So find here enemy controller and change the separation weight to, let's say, 0.3 only. This will apply to all of the enemies in the scene. You can also verify it. You can see all of them should have a 0.3 now. And play the game. Now the separation force is very small. And they are getting separated like this. Or maybe you want to increase the separation force, depends on proximity of the target and so on. But for example, this is already working really great, as you see here. And you can play with these values. So for example, maybe more alignment. So let's assign it to the 3 value. You can exaggerate these values to see how they are affecting really the enemies. Apply all alignment, and let's see how this will affect the enemy movement. You can see they are aligned with each other much better until they will group together in the player. But while they are running to the player, they are aligned better. Okay, and then let's say alignment will decrease to 1 as it was, and cohesion 3, and again apply all, and play it. And now they are moving again different. You can see how they went into the average position, which looked a little bit weird. We can even maybe decrease this to 0.5. A cohesion weight, maybe a little bit more alignment, so 1.2, and separation weight 0.4, and overrides, apply all, and let's try this. And again, maybe change the detection distance and all of these things. But now we have solid algorithm for following, and I think it's quite good. All right, so that's gonna be it. That's gonna be it from this video. That's how you will implement simple version of the boid algorithm. You can introduce more things, you can play with the values, but the results, as you see, the following of the enemies are now much better as we had them before. Okay, that's it from this video.